Any questions over Friday's discussion? Well, I might have some questions of my own at the end. Signals may be split by adjacent protons that are different from each other with different coupling constants. Now, if this was a single bond and we have a methyl group, we say all those protons are equivalent. Here we have a double bond, and these are locked in position, and so they are no longer equivalent, meaning this proton will have a signal, that proton will have a signal, this proton here will have a signal. And notice these two protons are only separated by 2 bonds. So we saw most of the splitting we observe is 3 bonds away. They're from protons on adjacent carbons. But here we see protons on the same carbon splitting each other. So here, this proton here is split by this proton, and it has a coupling constant of 17 hertz. And it's also split by this proton, and we have that 11 hertz coupling constant. Let me just back up to the coupling constant page. So these are kind of approximate, but that gives us a good idea. The one at 17 was trans, and the cis, they said, was at 11. You know, probably what else is bonded here, and we have that benzene ring, and we're going to find out that benzene rings are special because of those pi bonds and resonance and all those delocalized electrons. So here's the coupling constants and the different shifts on A and B. So here's an NMR spectrum of styrene. So as before, I'd say, how many signals do I see? This one might be a little tough. I think I see 1, 2, 3, 4 signals. We'll count the benzene ring as 1, 2, 3, 4. That almost worked. You know, there's going to be some exceptions somewhere. But this mess here, you look at it and you might say, oh, it looks like a multiplet. It doesn't look like a triplet, doesn't look like a doublet. And when it's blown up, it looks like this. So there's the J coupling values, and it's split by this proton and that proton. 1, 2, 3. Yeah, it's distance. We don't care what bond's there. It's bond distance. So this thing gives us a doublet split by that. Here is C, and we got B, and then A is what it is, and then the benzene. And I put these on the same slide, so hopefully we could make more sense of it. The 11 was the cis, and the 17 was the trans. So the J coupling can help you sort that out. I don't think I have any J coupling questions on any quiz. I'll have to check that. Now on to yours and mine favorite topic. That'd be stereochemistry. Stereochemical non-equivalence. So here's a good old ethanol. I see 1, 2, 3 signals. So these protons are all equivalent. So maybe this is one place where our textbook falls a little short. And it says, let's imagine replacing one of those hydrogens with an imaginary element called Z. I don't think there's one up there with Z. And we see that if this rotates around, it's the same compound. So it says if the replacement of each of the protons of a CH2 group with an imaginary Z gives stereoisomers, then the protons are non-equivalent and will split each other. And this is the slide they came up with, and that's a little strange. But we're going to go into better detail, and I'm going to make it crystal clear. One use of proton NMR is to ascertain the number of electronically non-equivalent hydrogens present in a molecule. In relatively small molecules, a brief look at the structure can help determine the kinds of protons present and the number of possible NMR absorptions. Equivalence or non-equivalence of two or more protons can be determined by comparison of structures formed if each hydrogen was replaced by some other group. We can call it X or Z. So here's just straight up butane. And how many signals should we see in a butane NMR? We should see 2, and what should the splitting patterns look like? I would say butane, there's my TMS. I'm gonna have a triplet, and then these two would be a quartet. Getting rusty with my drawing. And that's it. It looks like 2 ethyl groups stuck together, 2 different signals. Always good to review and get lots of practice. Right here it says CH2, the CH3 hydrogens are unrelated and have different NMR absorptions. And we just drew those absorptions above it. Now if we replace the methyl or the methylene with X, like so, now we have 2 different constitutional isomers. And that kind of tells us that why we'd get those 2 signals to begin with. When we look at the methyl protons, we say they are homotopic. That means they're in the same chemical environment and they give the same NMR absorption. And we said we get a triplet because they're split by 2 protons. If the protons are chemically identical, the same product would be formed despite the substitution. That means if we stick it over here on the right, we'd get the same thing if we had it on the left because it would flip around. So only one substitution product is possible. If the hydrogens are homotopic but not identical, substitution will form a new chirality center. Hydrogens that lead to the formation of enantiomers upon substitution with X are called enantiotopic. All right, so we got the butane up here again, and if I replace either the green or the blue, I get 2 enantiomers. So what that means is we say these protons are enantiotopic, and they have the same NMR absorption. Now we've just destroyed the symmetry of this molecule. We now have 2 butanol, and we can see a signal coming from that methyl, signal coming from that methyl, signal coming from that hydrogen. That OH hydrogen is going to have a signal. And if we want to describe those 2 protons, they now have a slightly different chemical environment. Why is that? The 2 hydrogens on this 3rd carbon are said to be distereotopic and have different NMR absorptions. Because if we replaced one of those with an X, some imaginary atom, then the 2 substitutions give us distereomers. These hydrogens are distereotopic. If I replace this one with something else, and then that one, I get a pair of distereomers. And that sometimes can help us out here. How many absorption will S-malate, an intermediate in carbohydrate metabolism, have in its NMR spectrum? What do you think? Not everyone shouted out at once. Normally you might say 1, 2, 3, right? But since this stereo center here, replacing either of these I could get in a pair of enantiomers. I'd get distereomers. Didn't want to mess that up. So how many signals? I just counted out what we normally might think, 1, 2, 3, but it's got to be more, right? It's got to be 4 signals. Signal from this proton, signal from that proton, and a signal from that one. They've counted them out. 1, 2, 3, 4. Because S. Yeah, it looks like S to me. I really like the hand rule. Hydrogen's going back. Hydroxide, this carbonyl carbon group. All right, because S malate already has a chirality center right there, these two protons adjacent to that are distereotopic and absorb at different values. And so the proton NMR spectrum of S malate has 4 absorptions. So I think with alkenes, it's easy to see. We already went through it a little bit with styrene. So here I'm thinking 1, 2, 3, 4 signals. I have 4 different types of hydrogens. Replacing the cis hydrogen gives the cis diastereomer, and replacing the trans hydrogen makes the trans diastereomer. Because the 2 imaginary products are diastereomers, these protons are called distereotopic protons. Distereotopic hydrogens are capable of splitting each other, give us 2 different absorptions. All 3 of these are in a different chemical environment. These 2 are in the same chemical environment. Bonds rotate around and they're indistinguishable. So here's a methylene group, and normally we would say this should give 1 signal, maybe split by that thing. But since it's adjacent to this chiral center, we say the 2 protons on the CH2Cl group, carbon number 1 there, are distereotopic. Their imaginary replacement gives diastereomers. So here they put this thing into a Fisher projection, and they say, let's substitute Z there. Let's substitute Z there, and what do we get? We get a pair of diastereomers. Distereotopic protons are usually vicinal, fancy word for the next carbon away, 1 carbon away, to chiral carbons. Use the structure below to state the relationships between the indicated protons as equivalent, which if we back up a bunch of slides, the homotopic would be a synonym for equivalent, but we have enantiotopic and distereotopic, or unrelated. So here we have 1 bromocyclopropane. And it says here, so we basically have, sorry about the poor quality of this graphic. I think this is A, B, and C. A and B are distereotopic. Imagine putting like a chlorine on here or a chlorine on there. Or we could even do bromine, but that would give us a pair of distereomers. Hard ones to see is an enantiomer. What could we substitute and get enantiomers? A and C. B and C, distereotopic. It's just the first example I could find, and it's not that great. So we'll move right along. But here's an example. Notice this carbon here has 1, 2, 3, 4 different groups. So we have a chiral center here, and normally you'd probably say 1, 2, and 3, and say I should just have 3 groups. 1, 2, 3, 4. And that's because these 2 are no longer chemically equivalent. They're chemically different. And we say they're distereotopic. That's what makes the difference. They're on a carbon adjacent to a chiral center. And like if we stuck an atom here and built another molecule and stuck a different atom there, the same atom like bromine or Z, imaginary element, we get a pair of distereomers. They're not mirror images. Well, with that all done, let's rationalize the splitting pattern. This looks like a doublet. You can barely see it. And so 1, 2, 3 bonds away. Here's this hydrogen, 1 hydrogen, splitting that signal into a doublet. this hydrogen here, it sees those 3 hydrogens and these 2. 3 and 2 make 5, n plus 1. 5 plus 1 is 6. That's this thing here. 1, 2, 3, 4, 5, 6. All right, now that we're done with that, let's move on to one of these. This thing, normally we wouldn't think it was split by that one, but now that we know they're distereotopic, I'm going to count that one. 1, 2, and let me just count bonds. 1, 2, 3, 4. That's 4 away. Here's where J coupling might help us out. I see the same J coupling there and the same J coupling there. The reciprocity. Well, we're going to leave that topic for now and talk about something else. Time dependence. Molecules are tumbling relative to the magnetic field. We can think that they're tumbling because typically we're doing NMR on a liquid. Molecules have some kinetic energy. They're not frozen in a solid. We might even think of Brownian motion. So an NMR is an average spectrum of all the orientations. Actual and equatorial protons on cyclohexane interconvert so rapidly that they give a single signal. Proton transfer for this hydrogen off of oxygen, because it's said to be acidic, or hydrogen on a nitrogen, occurs so quickly that the proton is not split by adjacent protons in the molecule. Remember a couple days ago when we did isobutyl alcohol and we had that nice peak split into 9, and I said alcohols were weird. So here is ultra pure methanol, and if we can get the methanol pure enough, we will see the hydroxy proton split itself, and we should see it be splitting other things on the ethanol molecule. Let me see if I can make a fool of myself. We should see 3 signals. Those protons, that one proton. And typically we'd say this is going to be split by those 2. N plus 1 says 2 plus 1 is 3. That's our triplet here. I don't know what that little artifact there is. And then this thing here, I ought to be able to go 3 and 1 more to get to 4. N plus 1, that's going to be 4 plus 1 is 5. 1, 2, 3, 4, 5. Sounds decent. This thing here, 1 bond, 2 bond, 3 bonds, those 2. That should give me a triplet. And that looks like a triplet. Once again, I don't know what that artifact there is. You got to work real hard to get an NMR spectrum of, I mean, you need some grad student in a glove box or a vacuum line to prepare this. Normal ethanol looks like this. And here they spelt it out for us. Here's the methyl group, a triplet, the most shielded out of everything. Right here, here's our TMF. And here, we just get a single peak. And here we get our standard quartet. So now I put these on top of each other so we could see. Here's our triplet. When it's not pure, we get a singlet. And then there's our quartet. So the pure, we actually see this triplet. Impure, this comes off because it's acidic. How many signals? 1, 2, 3. 1, 2, 3. That looks a little strange. So these, at least the first proton, should come off. The acidic proton on the nitrogen has a moderate rate of exchange, and the peak can be broadened. So ways to identify whether you have that in your sample or not. Chemical shift depends on concentration and solvent. To verify that a particular peak is due to a hydrogen on an oxygen or a hydrogen on a nitrogen, pour in some DTO, which is deuterium instead of hydrogen. This is heavy water. And over time, the acid-base chemistry does its thing fairly rapidly, and you will see the peak disappear. It says the deuterium is invisible in the proton NMR, so the original signal from the hydrogen on the oxygen will disappear. Now we want to go back to the first day of NMR class. What made a nuclei NMR active? Odd atomic number or an odd mass number. What's the mass number on deuterium? It's 2, and it's easy to think, well, it becomes non-NMR active, and that's wrong. So I wrote this the other night when I was working on these slides. Deuterium's resonance frequency puts it out of the size or range of normal proton NMR. It's still there, the signal's there, but it's, it's like your FM dial on your car. Maybe you don't even know what I'm talking about. It's like 89 megahertz and like 108 megahertz, and all of a sudden the radio station is beyond, to the left or right of that. So deuterium has an NMR signal, but when your machine's set up there to do a proton NMR, it's not in that range, and so it disappears.